Welcome to Two Bees in a Podcast, brought to you by the Honeybee Research and Extension Laboratory at the University of Florida's Institute of Food and Agricultural Sciences. It is our goal to advance the understanding of honeybees and beekeeping, grow the beekeeping community, and improve the health of honeybees everywhere. In this podcast, you'll hear research updates, beekeeping management practices discussed, and advice on beekeeping from our resident experts, beekeepers, scientists, and other program guests. Join us for today's program, and thank you for listening to Two Bees in a Podcast. In this episode of Two Bees in a Podcast, we are going to be speaking with Keith Delaplane, who is a professor at the University of Georgia. He'll be here talking to us about queen mating behavior. That segment will be followed by a segment that Amy and I are discussing the label. Have you ever wondered how to interpret pesticide labels, what they mean, and if you should follow them? Well, we'll be talking all about that in a segment called The Label is the Law. And of course, we'll be finishing today's podcast with our famous question and answer segment. Thanks, guys, for joining us on this segment of Two Bees in a Podcast. As far as I'm concerned, we have a very special guest with you today, with us today to talk about some of the things that he's been up to at his institution. He's special because many reasons. He's done a lot to accomplish things professionally for honeybees and for beekeepers around the world. But I also have known him for a very long time. I worked as an undergraduate in his laboratory for 4 years when I was pursuing my undergraduate degree at the University of Georgia. And then I came back to his lab and served as a postdoc in his lab for a couple years after I got my PhD. He was in my wedding, and most people who go to my wedding can remember the bagpipes. Everybody says, who was that guy who played the bagpipes? Absolutely, Amy. And I'm talking about none other than Dr. Keith Delaplane, professor of entomology, Walter B. Hill Fellow from the Department of Entomology at the University of Georgia. Dr. Delaplane, thank you so much for joining us on this podcast.
Well, thank you, Jamie. And I always say there's no event that a set of bagpipes can't make better.
That is so funny. You know what, Dr. Delaplane, I think your name has been brought up in probably at 75% of our podcast now.
Well, that's our point of reference, right?
That's a good sign or a bad sign?
And the funny thing is people at my wedding don't even remember me being there. It's just that they all remember the bagpipes played at the wedding ceremony. And Dr. Delaplane, I don't know if you know, but Amanda and I, we've been married for just about 18 and a half years now. So that was some time ago.
Oh, mercy.
It's crazy. Time flies. All right. So I've known you for some time now, I guess 20 plus years. And so I'm curious if you could tell the listeners a little bit about yourself, how you got into bees and beekeeping, and how you found yourself at the University of Georgia.
Well, I consider myself very fortunate that I was able to follow a boyhood hobby into graduate school and ultimately a faculty position here at the University of Georgia. I come from a farming family in Indiana. My family grew corn and soybeans and hogs. And my father grew up knowing about honeybees because his dad kept them. My dad did not have any interest himself, but for my 13th birthday, he thought it was a good idea for me to keep bees. And so I got a beginner's kit. And I think now in hindsight, it was a portent of things to come that the packaged bees in that beginner's kit came from Georgia. It was a sign of where I was heading. So I started off with 2 hives, and they grew to 4, to 8, 16. And I think the most I ever kept when I was growing up at home was 50, which is quite a bit for a young kid, but I enjoyed it very much. And then I was able to follow my interest in bees into graduate school, and I moved from Indiana to Baton Rouge, Louisiana, to attend graduate school at LSU under the direction of Dr. John Harbaugh, who was a honeybee breeder and scientist at the USDA bee lab in Baton Rouge. At that time, it was one of the few graduate research programs in the country. And after 6 years in Baton Rouge, then I took up my post here at UGA in January of 1990. And it's been a good career, not only working with the bees, the most fascinating animal there is, but with all of their beekeepers too, which are at least equally as fascinating people. And so here after 30 years, I'm grateful for that life trajectory.
That's amazing. I feel like we need to have you on to talk about the history of everything, that you've seen throughout your career, but we'll have to save that for another day. So we'll have to have you back on again.
We can do that.
Yeah, that's fair. So we actually have been talking a lot in our podcast. Some of our segments have been about queens. And I know when we had reached out to you, you said that you wanted to speak on queens a little bit and some of their mating habits. So that's what our segment is going to be about today. Of course, we'll have to bring you on again for another topic, but let's go ahead and start talking about honeybee queens. So can you talk to us about the process of what happens after a queen emerges from her cell?
It's pretty chaotic at first because these young virgins that emerge, and there's usually always more than one, it's a messy ordeal. And these young virgins do carry, each of them, a particular signature of queen pheromone, but it is not at very high levels yet. It doesn't reach its full levels of pheromone until after she has mated and begun laying eggs and function as a normal queen. So there's a lot of chaos. Different queens are trying to jockey for control of the colony, so to speak, and different workers don't really know where to give their allegiance. And there is outright fratricide going on because queens do not abide other queens, and so there will be queens going from cell to cell trying to abort their sisters before they can emerge. It is not a hierarchical process, one that is organized and managed and strategized. It is very chaotic. And there's many different factors that go into play of which queen wins. It could very much simply be a matter of whoever emerges first has, probably a statistical chance of succeeding in the end. And ultimately, she will kill her rivals, and she will fly and mate on the air, on the wing, and come back and hopefully resume the queenship of that colony. So it's kind of wild and woolly. It's fraught with error, and as any longtime beekeeper knows, a requeening event could very well go sour, and the colony simply fail to requeen itself. And this is where a beekeeper has to be vigilant and note when that happens and step in and try to salvage the situation by introducing a new queen.
I feel like this is always, whenever we talk about bee biology, people are always so interested in the politics of bees and the queen. And they, it's just a story that we tell about how this all happens. And I feel like this is everyone's favorite topic. As soon as you start talking about queens and their mating, it's like that's what, really pulls them in to start thinking about honeybees in general. What do you guys think?
It's true. I mean, you can't beat sex. Anytime you talk about sex, people's eyes are going to open wide and their ears are going to open. Well,
I was going to mention something similar, but I think my comment was going to be a little bit more diplomatic, for sure. I was going to say that sex definitely intrigues people, but Delaplane, you probably said it better than me.
Well, it is fun to say, but it's also true. I mean, think about it. In the history of life on this planet, sex has been one of the great success stories. It's testimony to how genetic recombination in various forms is adaptive. Organisms that have a lot of allelic diversity in their genomes tend to be more vigorous than those that are more narrow. So it's there's many good reasons why we're interested in sex, and it's certainly
just to name a few, right?
As well.
Well, that certainly leads me to my next question. And you'd mentioned that once the virgin queen emerges and disposes of her competition, she has to mate. Can you tell us a little bit about how that mating happens, the mating behaviors that queens and drones exhibit?
Yeah, it too is featured with a lot of chaos. The virgin queens are programmatic, and they do, after about a week of age, they have amassed enough strength and maturity and nutrition that they can start taking mating bouts and mating flights. And this is one of the best examples of where the entire species, the honeybee Apis mellifera, has gone to extraordinary lengths to create genetic diversity in the nests. The honeybee queen multiply mates, and we call that term polyandry. Poly means many, andry means many males, polyandry. The opposite of that is practiced by many ants and termites, polygyny. and that is many females. So a very large and spacious subterranean ant colony, for example, may have numerous little queens and queenlets, if we may, scattered across the realm. Polygyny is what we call that. Well, that doesn't work with the western honeybee that lives in a relatively small nest about the size of a couple basketballs. There's not enough space for a colony to endure numerous competing queens. So the strategy that the genus Apis has adapted is one queen mating with many males. So you see how the two strategies end up at the same place. Whether you have multiple queens or if you have one queen with multiple mates, either way, you end up with a social colony that is genetically diverse. And I think that's an important theme and why I have been interested so much in polyandry in the last few years is that the strategy that Apis mellifera uses to employ genetics is a strategy of diversity. Whether the queen mates multiply or not dictates how much genetic diversity is in her daughters. And colonies that are more genetically narrow do not perform as well ecologically as those with whom their queens have mated with many males. So getting back to your question about how does this mating occur, one way it happens is the queen's multiple mating habit. Well, that is only possible if the drones cooperate, and they do. They're quite happy to cooperate. And this is where we have that fascinating behavior called the drone congregation areas. And drones tend to cluster together. They tend to fly out on a good, warm, sunny afternoon, and they end up forming like rivers in the sky, avenues, highways in the sky where drones from multiple colonies converge and they start flying in circuits around the landscape. And these circuits tend to be very long lasting, year after year. And beekeepers who live long lives notice this, that these drone congregation areas tend to be constant. And this has been for a while a mystery of biology because we have no transgenerational learning. When a drone dies in fall, he's dead, and there's no way for him to transmit the knowledge of the drone congregation area route to next year's drones. Yet, that route persists year after year. How does this happen? Well, it probably happens because of the landscape features which tend to be permanent year after year. And so a drone flies out, he sees a light window in the horizon, he follows that dip in the horizon where the trees stop, and he flies in that direction because that's where the light is, and he goes through that light window, and oh gosh, look, here's the edge of a forest. Well, here's a strong visual. Let's just follow this edge of the forest. Oh, look. The edge of the forest comes to another edge along this river. Okay, let's follow this river. Oh, look, it comes back and encounters a cliff. Okay, we'll follow the cliff. And before he knows it, he's gone a circle and he's back where he started from. So this is probably the best explanation of why drone congregation areas persist year after year. Well,
I always kind of joke around and call it the dude bee bar.
The dude, you're not far because they're kind of like teenage boys cruising the strip, on a Saturday night, and just like the teenage boys, they probably have one thing on their mind. So you're not far from
basketball.
Basketball, that night's basketball game. Boy,
it's not basketball.
Beat them good.
That's Jamie.
Oh, okay. I'm sorry.
But what you get is, you get all these guys from all these different colonies. There was an interesting study done back in the 1970s in Germany, and they were able to show that an average drone congregation area contained males from over 200 colonies. So yes, it is the guys coming together and cruising the strip. And so it's these drone congregation areas that these virgin queens find, and it's very, very easy in some way, to copulate with many of them in very fast order. And so you have this elaborate behavior of the queen's native promiscuity that is co-opted with the drone congregation areas to result in queens mating with many, many males. Polyandry.
Interesting.
That's how it happens.
So you're talking about many males. I do get this question pretty often. People always ask me, how many drones do queens actually mate with? I've heard between 10 and 25. I mean, are there more? Is there less? Is there an average of, how many drones queens usually mate with?
Yes, there is. And there's actually quite a bit of literature on this. And a good review that was performed about 10 years ago by David Tarpey, who's our colleague at North Carolina State University. David found a species average in the literature for Apis mellifera at 12. 12 males tends to be a pretty robust average for what Apis mellifera mates with. She is by no means the champion in this respect. The giant Asian honeybee, Apis dorsata, has a species average of over 25. Wow. So honeybees, the western honeybee that we know, is kind of in the middle of the pack as far as the genus goes. And the numbers do range widely. The highest number, to my knowledge, again, comes from Dave Tarpey's lab. One of his students published a number of 77 males.
What?
Was recovered in one female. And this has been kind of, Amy, it kind of gets to the center of my research interest is, why does the queen mate with so many males? The literature in the last 10 years or so has shown a really strong relationship between the number of males that a queen mates with and the ecologic vigor of her colony. Basically, the more the better. And this I find interesting from an evolutionary point of view, but also for the point of view of beekeepers as we try to use genetics in our bees to solve the big health problems that we're facing today. And I think polyandry has been understudied, and we should pay a lot more attention to it in practical beekeeping.
So when you say more is better, what do you mean by better? What does that look like? What does that mean?
Well, good question. I did a sabbatical. It's been 6 or 7 years ago now with a colleague, Giles Budge, at the National Bee Unit in York, England. And we were trying to get an answer to that question, Amy. What are the upper limits? What are the constraints? And in our design, we used instrumental insemination. And yes, we can do this. We can instrumentally inseminate queen bees. And
that's another topic that we'll have to talk about.
Another topic.
Yep, exactly.
And a good one to cover. But we inseminated queens with the semen of either 15 drones or 30 or 60. We doubled it in double increments. And then we took those queens and established them in colonies, and we made several measures of colony strength. And we found pretty consistently that the 30 and 60 group outperformed the queens that had only been mated with 15. This raises at least as many questions as it answers. If the species average is in fact 12, as I said earlier, then we have to ask, well, then why do they stop at 12? If you get better performance at 30 or 60, what is to constrain them? And this has been kind of what we have been working on in the years, since I have come back.
So what's the answer to that?
Well, what's the answer? I knew you were going to ask that.
You can't leave us hanging.
Well, let's think about it. If evolution is a cost and benefit, a tension between the two, and it is not entirely risk-free for a queen to practice limitless mating. For one thing, just as there is with human populations in invertebrate populations, we also have sexually transmitted diseases. And we do know, for example, that deformed wing virus is transmissible in drone semen. So that creates one constraint. It may not be adaptive for a queen to just mate infinitely. Another constraint is environmental. Birds. Birds are serious predators. Navigation and flying. Queens are very bad flyers. A normal queen will only fly, 2, 3, at most maybe 4 episodes in her entire life. So these insects are very vulnerable to bird predation. So this creates a strong counterweight to whatever adaptation benefits there may be for a queen from a genetic diversity perspective. So evolution is all about optimizing these constraints, and this is probably why the genus or the honeybee has landed at about 12 as a satisfactory compromise between those two extremes. We have to ask ourselves, though, okay, well, just because we can say that, can we in fact show that? And if genetic diversity, and put quote marks around those two words, genetic diversity, if that's as important as we all think it is, then how in fact can we measure it? Well, this is stuff that geneticists can do. And Ben Oldroyd, who is one of our distinguished colleagues from the University of Sydney in Australia, has shown that a queen captures 90% of the genes in her mating population within her first 6 matings. 6! By her 6th mating, she has captured almost all of the alleles that are out there in her mating population. But yet, the species average is 12. Why do they do this? Why do they exactly double the number of matings that is necessary to acquire most of the alleles in their population? This is a big mystery. We think we have a good answer to this. There are some characters that are adaptive to the colony only if they are rare. Now that seems odd until a beekeeper stops and thinks about it. And Jamie and others who have worked in Varroa resistance, we have a really good example, Varroa sensitive hygiene. And I think any of my beekeepers out there listening who have used Varroa sensitive hygiene queens, you got to have a question. Why does this character disappear? You spend a lot of money, you buy a Varroa sensitive hygiene queen, and you fill all of your colonies with these VSH queens, and they might do pretty well for a year or so, but that trait vanishes. That trait tends to erode in the population. And you got to scratch your head and say, no, why does it go away? If this character is so valuable, if it gives honeybees resistance to Varroa mites, why in the world is that character recessive? Why is it rare? Well, this is a perfect example of that rare allele model that I'm talking about. And there was a group in Germany who proposed this and said there are certain traits that are only beneficial when they are rare because they are so potent that if they were dominant, that they would overwhelm the entire colony with one behavior, and the colony would not be any good at anything else. I have an example. It is possible with Varroa sensitive hygiene to get overexpression of this character so that the worker bees actually abort all of their brood, not just the brood that has mites, all of it. They go crazy. They can't stop pulling out brood. Well, this is too much of a good thing. And so Varroa sensitive hygiene is an example of one of these rare alleles that's only beneficial in very small doses. It's kind of like Tabasco sauce. A little bit is what you want. You don't want to you don't want to have some rice with your Tabasco sauce. You want it the other way around. And VSH is one of these characters. So our latest research has shown that these characters express under conditions of polyandry. So even though a queen may capture everything she needs genetically within her first 6 matings, she has to go beyond that to capture these, I call them the brass rings, those really extra special characters like Varroa sensitive hygiene. She has to go above and beyond the 90% plateau to capture those. And that is kind of our best understanding of why queens mate at such extraordinary numbers as 77, for example, that are outrageously beyond what the mathematics of genetics would say they need to.
That's just pretty fascinating. I was fortunate to be able to work with Nico and Gudrun Kerniger and Larry Connor to write a book, Mating Biology of Honeybees. And I just became fascinated with how this whole process happens and how complicated it is and how they pull it off and the benefits, as you note, of polyandry. But there's other questions and other issues that they face as well. Because, queens should not mate with their brothers, right? Inbreeding is bad even in the bee world. But when they go out on these mating flights, if there's a low density of colonies in the area, it's possible that there's potentially a lot of drones at those DCAs that are related to the queen. So do queens mate with drones from the colonies from which they originate? And if not, how do they prevent inbreeding?
Excellent point. And I think the answer is they most certainly do. The answer is yes, they do mate with very near kin, potentially even brothers. It could not be, I suppose, no, it could not be a son, because a queen would not have lifespan enough to produce matured sons to fly out and mate with her. But it's most probable, almost absolutely certain, that she does mate with brothers. And I would argue that this is probably yet another adaptive character for polyandry. You can kind of think about it this way, yeah, sure, I get a few bad matings, but if I mate with enough others, then it'll just sort of cancel out and it won't matter. I think that is another explanation for the evolution of polyandry. I think it's probably safe to say too, and I'm parroting a comment by Rob Page on this, that it may not even be a product of natural selection. Rob Page and Dave Tarpey have put forth the idea that it may be a completely stochastic, random event, which, when you think about it, is not entirely out of the question. I mean, with the drone congregation area that I described earlier, I mean, we're not talking about an orderly affair here. I mean, this is a mass chaos and pandemonium. And a queen has, conceivably no control over which of those males she's mating with, nor how rapidly she mates with them. And so the outcome just may simply be an outcome of chaos. I tend to not believe that. I do not believe that. And the reason is because we have been able to show colony adaptive benefit at extremely high levels of polyandry. So I personally do not believe that scenario. But it is out there and people are talking about it.
That's interesting. So I'm going to assume you were talking a little bit about artificially inseminated queens and what you're doing for your research. And of course, we're talking about queens that mate in the wild. I would assume that there are differences, but can you talk a little bit about maybe the differences in queen quality, or, what kind of outcome, if there is a difference, and what are the differences between the two?
Yeah, that's a good question. Instrumental insemination is a tool that I strongly believe in, and I encourage beekeepers to consider learning it. I encourage beekeeping clubs to invest in it. I acknowledge that it is daunting, that to an individual, the idea of learning this skill and buying the equipment is intimidating. I mean, we are talking probably in the neighborhood of $1,500 to $2,000 investment. And that does not cover whatever training the individual may need to get. But for some,
we all have that to throw around.
Sure.
The extra cash, yeah.
Yeah. Well, some people do. Some clubs do.
Stimulus checks. Everybody should run out and buy an instrumental insemination device.
I was going to say, yeah, that's right. Stimulus in more ways than one, right?
There you go. You said it, not me.
You're leaving all those juicy comments to me.
Well, I work for the state, and I'm not allowed to say certain things.
Bring in the out-of-state guy to say the stuff.
That's right. Yeah, you're the one who gets in trouble, not me.
But no, I think clubs do buy equipment for their members, like honey extractors, and I think this falls right into that kind of line. I could see some of the more larger and active clubs, buying an insemination device and even paying for some of their members to get the training. Certainly, absolutely, queen producers and breeders should have this skill under their belt. And it is the only way to guarantee targeted matings in the honeybee. There is no other game in town. It is the only way to control mating in the honeybee. And so for this reason, it's highly valuable. Back to your question, though, Amy, the differences between the two, there do seem to be some differences. I think there is a great deal of handler skill that expresses itself. If you're clunky with the queens, if you don't really know what you're doing, the outcome will show it.
Sure.
It's a thing where a lot of practice helps. You cannot be more. You cannot be too tender and gentle with the queens. The queens need lots of attention by workers and nurse bees before and after the procedure. Sanitation is extremely important. When we're inseminating queens, it's kind of like COVID-19. We're constantly sanitizing every surface we touch.
Sure.
In between the queens to eliminate.
Do you give her an epidural or?
We do of sorts, and that's a big blast of CO2 in the face. Carbon dioxide narcotizes insects. It knocks them out. We don't really know if they're unconscious or feeling pain. I mean, quite frankly, we don't know that, but it does, anesthetize them so that they're immobile. Otherwise, their muscles tense up, and we would not be able to inseminate them under the microscope as we do. But there do seem to be performance problems. Instrumentally inseminated queens generally do not do very well as production queens. They're fantastic for breeders to have a well-mated mother that can produce daughters, and then those daughters are then open-mated. That's normal in the U.S. queen production industry. Most queen breeders will buy an instrumentally inseminated queen mother, and then they will rear daughter queens from that mother, but those daughters themselves are just open-mated, and it's kind of hopeful that they'll mate with the good drones when they do that. Zero control, in other words. But that is, nonetheless, the industry standard that we have right now. Sue Kobe, Joe Latshaw, other individuals who are out there that do this a lot, tell me that they can produce inseminated queens that are every bit as good as naturally mated queens. And I believe them. I think they probably can. I'm not that good. I inseminate maybe 100 queens a year, and that's nothing compared to what they do. So there are some performance problems, but keep in mind, what are we doing it for? We're doing it usually to get a mother from whom we graft queens. So it's a technology that's out there. It's an innovative technology. There's Apis Engineering, a new firm up in Indiana that's producing some very nice insemination devices. And I encourage beekeepers to check it out and learn it. It's not that hard to learn. Getting good at it may be hard, but learning it is not that hard.
So, Dr. Delaplane, this has been really fascinating talking about all the queens, the queen mating, and all of the research that you guys have been doing it. But I don't really want to end this interview until you have an opportunity to just kind of briefly discuss what you guys do at the University of Georgia. I mean, UGA is a land-grant institution. You guys have responsibility in teaching, research, and extension. So you've shared a little bit about your research, but can you give us just highlight of some of the other programs that you have going on at UGA? Our listeners are definitely going to want to visit your website. We'll make sure and link everything you've said in our show notes today, but they might want to hear it on the air as well.
Sure. Well, I think I kind of mirror what many of my peer labs across the country, including yours, Jamie, the kind of activities that we do in colleges of agriculture. We are somewhat unique in that we have clients. We have a client citizenship, and that in our case is beekeepers, crop growers, anyone who's interested in pollination and pollinators and pollinator conservation. And these are our clientele groups, and we try to address their interests through research and through continuing education and in classroom teaching. And so we wear those three missions with some tension, because you cannot do 100% of any one of them, though at times it feels like it. We try to do research that is addressing big issue questions of the biology and the evolution of honeybees, like we've talked about in this podcast. Why do queens multiply mate? But then I always feel in the back of my mind that my work is not really finished until I have translated that research into something that is useful for beekeepers. And again, in the case of polyandry, a perfect example, I really should not leave it just at that. I should instead try to take that knowledge about polyandry and use it for improving queens genetically for the good of beekeeping and beekeepers. And so we, for example, are looking how does polyandry interact with varroa-sensitive hygiene traits? How does it interact with grooming traits? How does it interact with Russian traits? How does it interact with other characters that honeybees are selected for? I think the whole realm of genetic selection has not interfaced well with polyandry, and that's what we are trying to do. So in the biggest sense, we take our research, we take our scholarship, and we try to translate it and deliver it to beekeepers and those who are interested in it. One of our biggest events of the year is the Young Harris Beekeeping Institute, which is similar to the Bee College that you have initiated, Jamie, in Florida. And we have it every May, unless COVID comes around and interrupts our plans, as it did this year. We have it every May at Young Harris College, which is in the extreme north of Georgia, up in the cool mountains. And it's a very popular event. It's a tourist destination. And I certainly encourage our listeners to check out the Young Harris Beekeeping Institute and come there and hear beekeepers from all around the world talking about science and the practice of beekeeping. So that's it. That's what we do in a nutshell, and we do all of it. I like to think that I do all of it well, but sometimes it's hard. You do extension a little more this month, and then a little more research that month, and you have many people clamoring for your attention, but it's exhilarating, and you meet a lot of wonderful people along the way.
Well said, Dr. Delaplane. Thank you so much for joining us.
My pleasure. Thank you, and hope to do it again.
Absolutely. Everyone, that was Dr. Keith Delaplane, Professor of Entomology and Walter B. Hill Fellow, the Department of Entomology from the University of Georgia. Fortunately, Amy, no old Jamie stories came out. Dr. Delaplane's known me a long time.
That's for a different segment.
Fortunately, we survived this segment without anything embarrassing to report on me. But it was a great segment.
You were worried the whole time, weren't you?
Well, I was a little bit nervous, but I'm pretty squeaky clean, though, so there's not much you can talk about. Anyway, Dr. Delaplane, thank you for joining us. We look forward to having you back.
Okay, my pleasure. Thanks for having me.
For more information about this podcast, check out our website at ufhoneybee.com.
All right, so Jamie and I are going to be talking in this segment about something that we always say over and over and over and over. Jamie, do you know what I'm about to say?
Get away from me.
Do you say that to me often?
No, we didn't necessarily say we say it to each other. We might use those phrases a lot all the time. You get away from me. No,
okay. Well,
I do know what you're going to say because we talked about this pre-show, Amy. How am I supposed to act surprised? What, Amy, what
I know. I just wanted to know what you were going to say, which that was pretty funny. Okay. So we always say the label's the law. We're always, and not just us. That's not we didn't make that up. I learned that, through the extension world. I've learned that just by speaking to researchers, industry, everyone knows this. The label is the law, right? So we wanted to talk a little bit about that today, what that means. And to be quite honest, I hate reading labels, and I feel like they're so complicated and complex. And I love plants, and I have to fertilize plants. Yeah. And even adding fertilizer is like just a headache.
Well, let's start a little bit from the beginning. So let's just make the point that we're talking about pesticide labels here, right? So, Amy, you are 100% right. if you are going to do pesticide education, your administrators, your bosses, your teachers, whoever introduced you to this topic, they are going to preach to you maybe a zillion times over, the label is the law. The label is the law. We just all know that. We know it. We hear it. We know it. It just on and on and on. I've heard my colleagues at UF say it. I've heard my colleagues around the world say it. It's just what people say. But what it simply means is that the label that is included with or on the pesticide product that you use is literally a legally binding document. You are supposed to follow that label. Failure to follow the label is to break the law. The label is the law. And, neither you nor I are pesticide specialists. The University of Florida has a pesticide office here actually to help us with a lot of these issues. In fact, in the show notes for this particular segment, we'll make sure and link the pesticide office because they have written a bunch of documents about pesticide labeling, understanding the label. The label is the law. I mean, there's documents explaining every part of the label, but it's important to know that the beginning premise of using any pesticide is the label is the law. Whatever you put into your colonies, you've got to follow the label. If you are putting things into your colonies that aren't labeled for use in colonies, you're breaking the law. And so this is a very strong statement. The label is the law.
Yeah, so I guess I'd like to take a look from the outside in. So I guess, just starting from the beginning, what is a pesticide? And, a pesticide has different kind of categories, right? So we have like fungicides and we have insecticides and can you start with that?
That's exactly right. So we tend to use this umbrella term pesticide, and it's any product or compound used to control a pest, right? And so insects can be pests, rodents can be pests, fungal pathogens can be pests, plants can even be pests, right? And so oftentimes, not oftentimes, we have these terms, these categorical terms for the types of pesticides. Insecticides are used against insects. Rodenticides are used against rodents. Fungicides against fungi. Herbicides against fungi. It depends on where you in the world you are. Fungi, fungi. I'm a fungi. Anyway.
I had a feeling you were going to say that.
Fungus. There's a fungus among us, which is always true because there's always fungi around. Fungi, however you want to say it. I'm an equal opportunity speaker here. However it can be said, I'll try to say it. No,
that's
in all seriousness. So all of these things have their own sides, right? And insecticide, rodenticide, fungicides, et cetera. So these things are things that are designed to control those particular things. And oftentimes control can mean death. When you're putting out an herbicide, you're usually trying to kill the plant that you're spraying. When you're putting out an insecticide, you're trying to kill the insect that you're putting out for which you're putting out the insecticide. So all of these things, these products that you will use to control these pests will have a label. The label will physically be on the bottle or the packet. The labels are also usually downloadable online. And the label is composed of federally mandated sections. There are things that have to be on labels. The active ingredients, the inert ingredients, the safety comments, the environmental hazards, the directions for use. All of these things have to be on the label. And the label, of course, that's the instructions for us if we elect to use compounds. Even the things that we put in bee colonies, they all have labels. And you were mentioning early, Amy, that a lot of labels can be difficult to understand. They certainly can be. A lot of label, in the bee world, we're relatively fortunate. You take a product like Apivar, it's amitraz that's essentially impregnated into plastic strips. And it's real simple because you follow the label says put so many strips in so many boxes, whatever. But a lot of these things are calculation. You'll get a vial of dust and you've got to weigh out that dust and mix it in so many gallons or liters of water, and then only so much of that can be put out per acre or hectare. And it's very complicated. Usually people who are putting out pesticides for a living will have to get pesticide use licenses, and they'll have to go through lots of trainings. They'll have to take continuing education units to keep those licenses, et cetera. So they can be complicated labels, and you really should ask for help if you don't understand a label.
I mean, more is not necessarily better.
That's right. we in humans have this mindset, we'll see a roach in the kitchen and it'll say, this treatment might say, well, put, 1 gram of this compound out and that'll kill all your roaches. Well, if 1 gram works, 100 grams will work 100 times better. But to use that product in a way that's inconsistent with a label is a violation of the label. You're breaking the law. Mm-hmm. So this sets a bigger stage for, I think, that's something important to hear. You and I, Amy, work for the University of Florida. It's a land-grant institution. It's a state institution. It's a very public position. We've got colleagues around the U.S. who work for land grants. We've got colleagues around the world who work for university equivalents or other agencies. And we at the University of Florida are often encouraged not to give specific recommendations regarding the use of a compound. Again, I'll pick on Apivar, the amitraz compound that we use to control varroa. It would not benefit me and you to talk about, well, I think you put 2 strips in per box, et cetera, because labels change. And if I've told people you've got to put 2 strips in a box, and now it's 3 strips in a box or 1 strip per colony or whatever, then I'm making recommendations that are contrary to the label. Sure. So that's why you will often hear people, Amy, like you and like me and our colleagues around the world, not make very specific statements about how to use a compound. Instead, we say you should consider using this compound and follow the label.
Sure.
Follow the label, right?
Yeah.
Follow the label.
I mean, you and I, so when we were kind of talking about segments and things that we wanted to discuss with our audience, at first I was thinking maybe we should go through each label, right? And read it and try to figure it out and kind of tweeze through. I'm going to let you make fun of me every time I say a word, but I just want you to notice that I'm calmly letting you say words that sound goofy. You just take it away. Everyone knows what I mean. So going through the label and really trying to understand it. But then the more we started talking about it, the more complex that was going to be, because we want people to be able to listen to our podcast later, look at a label and not say, wow, they were totally wrong, because honestly, we might be sometimes, just because things change so quickly.
Exactly. Plus, there's a lot of there's enough compounds out there that I've quit even trying to memorize the label. What I usually do for recommendation's sake is I'll say, if you're trying to control varroa, these products are available. Make sure you follow the label if you elect to use them. And the questions I much prefer to answer, well, what's the efficacy of these products? If I'm going to use it, what kind of knockdown can I expect?
Sure.
But the thing is too, Amy, is that labels don't just tell you, how to use it. It tells you safety that, is supposed to use. A lot of people ignore the fact. People love to use oxalic acid, for example. But if you look at the label, it talks about all this protection equipment that you're supposed to wear. And again, I'm not going to get into detail with it specifically, but there's a lot of compounds for which you're supposed to wear gloves or goggles or respirators, and not like these little, grass cutting respirators you'll put on your face to keep the dust out, like legit respirators that have to be, leak tested and all these things. And, and that stuff's called personal protective equipment in the biz. We call it PPE. So you're supposed to be wearing PPE when you use a lot of these compounds. And, it's safety for you. It's safety for the bees, and it's even things like withdrawal periods. A lot of these things have to be out of hives so long before you super those hives for honey production, or a lot of them can't be used during honey flows. And all of this is specified on the label. It's there in black and white, what you can and can't do, when you should and shouldn't use it, how long it can stay in, et cetera. And again, it's simple things. People will say, oh, it says stay in 56 days. Well, if 56 days is good, 112 days is better. But the reason it's 56 days is because research has shown it's useful up until that point. But afterwards, it loses its efficiency or so forth. So all of these things, even disposal. You shouldn't take these strips out of hive and just throw them on the ground to let earth swallow it. Even disposal for these things, and disposal for the packaging is included on the label, how you're supposed to handle all of this stuff.
Yeah. So what advice do you have for, the common folk like me?
What I always
having issues reading the label.
This is great. It's a great question. What I always tell people is that if you run into label related issues, at least in the United States, we have a fantastic team of county extension agents around the countries who live in the counties where you are. And a lot of these men and women have been trained to read labels, to interpret labels, and to even teach pesticide-related courses. So if I were in the U.S., and of course I am, I would check with my county extension agent. I live in Alachua County, Florida. I would go to the Alachua County extension agent and say, hey, look, I'm struggling to understand this label. Can you help me interpret? And they would help. They'd either be able to answer themselves, or they'd be able to help me find someone who could answer. Now, if you're outside the U.S. and you're listening to this, I would start, since this is a beekeeping podcast, I would start with your local, regional, state, provincial, or national scientist related to bees or beekeeping. I would say to them, hey, look, I'm trying to apply this to try to get this result. I've run into a hiccup. I don't really understand the mixing instructions on this label. Can you help me understand? And I think your scientists and your bee professionals, et cetera, they'd be able to help you interpret that label. But it is important to interpret it correctly and use it correctly because, at least in the U.S., failure to do so and you're violating a law.
Sure. Yeah. And I feel like it can just seem kind of daunting at first. When you're first reading, it seems like there's so much going on. I mean, it just seems like there are a lot of different steps. So
you are so right. And the crazy thing is I happen to know a mess load about, pesticides. We do a lot of tox work in the lab, and it's very common for me to purchase compounds to use around my property for whatever reason, and me to struggle understanding how I'm supposed to use a product.
Yeah.
Labels for use, directions for use, how much you're supposed to put out, how much you're supposed to mix, all that stuff can be confusing. That's why it's helpful to have those resources that we've mentioned.
Yeah. So go find help.
But I will tell you though, Amy, as well, is I can't stress enough that our own pesticide office here at the University of Florida has produced so many good resources. We'll make sure and link that again in the show notes so that you listeners can get to that. But there's a few things that I want to point out. A lot of people, there's lots of issues to talk about with the label, so we could go on for days. But one of the things that I want to think about is a lot of people, for example, I'll use Varroa as an example, are afraid to use any insecticide or miticide or whatever in honeybee colonies. And a good example is Varroa, because Varroa is a mite that you have to control with a miticide in an insect colony, right? So a lot of people are anxious about using some of the Varroa treatments in honeybee hives because they're worried about the impact of those on colonies. But you've got to know that labels were developed in a way to maximize the impact on the target organism, but minimize the impact on the non-target organism. So following the label means that you are maximizing the impact on Varroa while minimizing the impact on bees. In other words, it's safe to use. So what I would tell people is that even labels that are used on orchards or fruit and vegetable crops that honeybees are visited, those things are developed, believe it or not, with honeybees in mind. And a lot of times the bee kills that we get are not because a particular compound is harmful for bees, but it's because it was applied inconsistent with the label. If it had just been applied according to label, the bees would have been safe in a particular instance, but it was misapplied. And so as a result, you get collateral damage. Pollinators might be killed, et cetera. That's why as beekeepers, we need to work with growers, et cetera, to make sure they are following the labels, because the labels for those compounds, the things that will be used around our beehives, were developed in a way to maximize the impact on the target organism, but minimize the impact on things such as bees.
Yeah. And I mean, that's the same with residential areas, right? I mean, not just growers, but, your neighbors in a residential, or if you live in an urban area.
Well, it's funny. I'm glad you brought that up, Amy.
Yeah.
One of the things that people often want to blame bee kills on pesticides. And if it's pesticides, they want to blame those on ag settings. But in most instances, and that I'm aware of, the ag appliers are specialists in reading and interpreting labels. If you talk to a lot of the toxicologists for some of the big manufacturers out there, they will argue that some of the most rampant misuse and failure to follow label is actually the homeowner and not ag, because ag has long histories of trying to do this right and interpreting labels appropriately. So you're right. It's a good point.
Yeah. And we're not trying to point fingers. So don't email us being angry, because we're just here to share the knowledge.
I think one thing that's important to come out of this too, though, Amy, is if something's not labeled for use in bee colonies, we should not be using it in bee colonies. This might be throwing fuel on the fire, but part of our Varroa issue today is related to misuse of the compounds that we've had available to us, as well as bringing in compounds that aren't labeled for use in hives. That should be a no-no. Our industry should have never have done that, but we have, and here we are. And it's led to a lot of the Varroa-related issues we have. We now have a mite that's somewhat difficult to control. We have limited options. There's potentially, off-label use. And even that's the crazy thing. And I hate to point out this specific example because we might get hate mail, but, Amitraz is labeled for use in colonies as Apivar. But it's not labeled for use in colonies as other products. So even if the active ingredient, in this case Amitraz, is allowed to be used in colonies, it's only allowed to be used in colonies under certain formulations, in this case Apivar, and not in others where you go and buy a big tank of Amitraz and mix it yourself. Even though that's Amitraz, that's not a labeled use, and that's illegal. So that's an issue that we have to address as beekeepers. We have to be honest with ourselves and try to address this. And I know a lot of beekeepers feel pushed into a corner because there's so few things available for use against Varroa. But I would argue we need to spend our energies trying to find new things and not our energies into developing compounds, new ways of using compounds in ways that are violations of the label.
Well, I feel like there are two things that come up to mind when you're talking is one, we definitely have to have someone on the podcast that works with labeling. And I would love to understand the process a little bit more because I don't really understand the process to begin with. So it'd be kind of cool to have someone. So we'll try to find someone to come and talk to us about that process. But two, I think that this is a really good opportunity for collaboration. There's so many different entities that can come together, beekeepers, the EPA, research universities and land-grant universities, other institutions. I just think that there's a really great opportunity for collaboration for a lot of this applied science.
Absolutely. I agree completely. And, it's funny that all this conversation was just born out of, having a comment early on to us about, understanding the label. I think you even got an email recently about a label of a product that was difficult to understand. And there's just so much to know about labels. Number one, like we said early on, the label is the law. Failure to follow, it's a violation of law. Number two, labels have everything you need to know about that product, how to use it, how to dispose of it, the personal protective equipment, and on and on and on and on. Number three, the labels are developed in a way, like I said, to maximize the impact on the target organism, but minimize collateral damage. Number four, using the same active ingredient a different way is a violation of label. If it doesn't have honeybees on it, as an example, you shouldn't use it in or around honeybees. And so there's so much to know about this topic. That's why, Amy, we spend a lot of time talking about it at our bee colleges and things like that. In our Master Beekeeper program, we make sure and have modules on understanding labels. In fact, I remember narrating a whole module on understanding pesticide labels, and it dealt with all of these issues. We'll make sure and get some good links in the show notes so that our listeners can have some good resources to go back to visit when they're struggling with this particular issue.
Yeah, and I would also encourage our listeners to go back and listen to our previous podcasts. I think we interviewed Judy Wu Smart. So Dr. Wu Smart had helped us and kind of spoke to us a little bit about pesticides as well. So, again, this isn't the first and won't be the last time we talk about this, but we thought it was important enough to bring it into a segment.
It's everybody's favorite game show, Stump the Chump.
Hey, Jamie.
Hey, Amy.
I have a joke.
Oh, no. You've been saying, you didn't even tell me behind the scenes that this was going to happen. I'm a little nervous about what's going to happen. All right.
What is mold, honeybee larva, and honey moisture content? What do those have in common?
I don't know. Tell me.
They're going to be on this question and answer segment.
Oh, you're so smart.
Okay.
Actually,
so
I chuckled.
Thank you. I hope
Out
the
of
audience did
necessity,
too. They probably just feel bad, but I'm not going to question why everyone else chuckled. All right. So the first question we have for a question and answer is there a way to control mold in a hive, and how can someone prevent it?
That's an interesting question. I don't think I've ever been asked that question before. Usually, I see mold under a couple of scenarios. Number one, there's almost always a ventilation problem. Maybe the entrance is restricted. Maybe there's no upper entrance, et cetera. Oftentimes, colonies that are stored fully in the shade or colonies that are in low-lying areas where a lot of cool, moist air settles, those colonies will often have mold inside the nests. I will also say that when a colony is too small to occupy the nest in its entirety, in other words, you've got like more boxes or more supers on the hive than the colony can adequately cover, I will sometimes see mold in those combs that are unprotected by bees. So then, if you think about how to keep colonies from having mold, you just do the reverse of everything that I just said that leads to it, right? Number one, you don't keep your hives in low-lying areas where cool moist air will accumulate. You make sure that the colonies get some sun throughout the day, that they're not fully in shade. Also, you want to make sure that they're adequately ventilated. The way that I do that, of course, I have the colony entrance, the hive entrance where the colony can access. But at the very top, my covers have a notch cut in the inner cover so that air can escape a little bit through the top. Of course, I use the outer and inner cover system. A lot of beekeepers use migratory lids, but you can always crack the migratory lid just a little bit to allow some airflow. If the bee's gumming up with propolis, you can open up again. I even had a colleague who would put a small block of wood under his lid. If he had the telescoping lid, he'd do that just to make sure there was adequate airflow, out of the nest to vent that moisture that sets up the condition for mold. And of course, the last way is to make sure that your colony is strong and that it occupies the entire nest. So if you have frames that are unprotected by bees, if you have supers that don't have bees in it, you just take that off, because where there's bees, there's usually no mold problem. So all of those things can really go a long way helping to remedy this situation.
Yeah, so just not providing them the environment that they need to grow.
That's exactly right. That's exactly right.
Great. All right. So the second question we have is, how can you tell the difference between wax moth and small hive beetle larva?
That is also a really good question, and it's a little tricky to explain unless you're an entomologist. So before I start, I will tell you that people have battled with this question for a long time, so there's a lot of really good web resources. If you just Google wax moth larvae versus small hive beetle larvae, you're going to get a lot of images that show them side by side, and it's going to point out some of the features that are more obvious. So let's just start at the beginning. If you're working your way from the oldest of larvae to the youngest of larvae, it's pretty easy to tell a wax moth larvae from a small hive beetle larvae because they're so much bigger. Now, of course, the real problem lies when they're both small, right? Wax moth larvae also start small, and so they will progress through the same sizes that small hive beetle larvae will progress through, except small hive beetle stop and wax moth larvae keep growing. So the better question is, when they are the same size, how can you tell the difference between the two? And the key difference, there's two key differences.
You ask them.
That's right. You ask them, of course. Well, are you a beetle or a wax moth? And of course, they'll volunteer that information. No, in all seriousness, small hive beetle larvae have spikes on their various body segments. They run down the back of that beetle larvae. So if you Google a picture of a small hive beetle larvae, you'll see those spikes protruding out of the top of the larvae from every body segment. The other thing that helps is that both of them, both wax moths and small hive beetle larvae, have 6 legs that are essentially the rudimentary legs that will become the legs on the adult insects. And those legs are towards the front of the body, just behind the head. They're on the segments that will be the thoracic segments when these individuals turn into adults. But that's where it stops for small hive beetles. Small hive beetles have no more leg-like appendages further down the body. On the other hand, wax moths have what we call prolegs. This is very common in moth larvae, the things that we call caterpillars. They'll have this second set of legs somewhere midway to the body and further down the body. So essentially, they both have those 3 pairs of legs towards the front of the body, but the beetle larvae have no more legs, and the wax moth larvae have multiple pairs of prolegs or rudimentary type legs further down the body.
That is so cool. I would encourage all of our beekeepers, when they see the larvae, to look at the legs. That's awesome.
That's right. That's right. And so again, to get a good idea of this is just Google wax moth larvae versus small hive beetle larvae, and you'll see very clear direct comparisons between the two.
Neat. That's awesome. All right. So for our last question, how do you deal with high honey moisture content?
So Amy, I'm going to assume that the individual asking that question is asking about moisture content after the honey is extracted. But let me just make a couple quick statements. We want the moisture content of honey to be somewhere between 15.5% and to 18.5%. That's kind of the ideal moisture range for honey. Now, nectar, the bees collect this sugar water, this nectar from flowers, bring it back to the hive. They put it into cells. And when they bring it back to the hive, it's somewhere around 70 or 80% moisture. So a lot of that water has to be evaporated in order to condense the sugars, essentially evaporate off the water so that you've got a more sugar-like substance. And that special range is between 15.5 to 18.5. If honey is below 15.5 water, it's prone to granulation. It's prone to, coming out of solution, and you'll get this solid sugar being made as a result. If it's above 18.5% water, it's prone to fermentation. So you really want to have it in that range. So how do we make sure that happens? Well, number one, bees tend to cap the honey when it is within that range. So the first thing you should do is avoid extracting frames that have a large percentage of uncapped nectar. The general rule of thumb is you want 80% of a frame or more to be capped before you extract that honey. That way you're hoping that the bees are essentially telling you that this is ready.
Yeah, and that's on both sides, right?
Exactly. Yeah, exactly. So some people will take a super and they'll go, well, I've got 5 frames that are fully capped on both sides and these other frames aren't. But don't worry, the 5 frames that are fully, no, that will not work. You need to, every frame that you extract has to be at least 80% or more capped on both sides. Assuming that doesn't happen, a lot of beekeepers will actually take their supers off. And if it's not capped enough, they'll keep it in a small room where they run a fan, a heater, and a dehumidifier to draw off some of that moisture over a couple of days or a week. And they'll use a refractometer, which is a little device that you can use to measure the moisture content in the honey. So they'll check the honey that's uncapped to make sure it's dropped below that moisture content, and then they will extract it. So essentially they're drying off their honey. Once honey is mass extracted and physically in a tank, it is much harder to evaporate off the moisture, to dry it off, as it were. I know some beekeepers who put bubblers in the honey to dry it off, and while they're kind of bubbling through these settling tanks, they'll heat it and they'll have dehumidifiers in the room. I know of at least one equipment manufacturer who actually makes a dehumidifier. You can hook a hose into a drum of honey. The honey will be pulled through this dehumidifier machine, and out the other end comes honey that's a few percentage points lower in moisture. So the real key to it is not trying to solve the problem once it's extracted. It's trying to address the problem before you ever have it in the first place. And that's by making sure that you extract, fully capped or nearly fully capped frames of honey. Or if they're not, making sure that you try to dry it for a few days or a week. The only catch to drying it for a few days or a week is you're leaving frames of honey unprotected, available for small hive beetles. So you're going to have to make sure that small hive beetles aren't a problem while your honey's drying. But you really want to address these issues before you get it extracted, because it's easier to deal with them at that point. One key thing that people do is once you learn your honey flows, so let me give you an example of what I'm about to say, Amy. Imagine that your honey flow is 4 weeks. And it's going really well. And honey's coming in, you put super and super and super in, and it lasts about 4 weeks. And at about week 3, you've got 2 supers on that hive that bees haven't quite moved into yet. Rather than saying, I hope this last week is great and they're going to move up into it, take off those 2 supers so that the bees will use that last week of incoming nectar to fill the available cells and cap it off. The worst case scenario is that they move in those upper 2 supers, start putting a little bit nectar in there, and then the honey flow stops and they've got no nectar to finish filling that, capping it, and all of that stuff, and you end up with a lot of uncapped stuff that's not quite ready to be extracted. So a lot of beekeepers try to force their bees kind of down into fewer supers as that honey flow wanes, just to make sure that those supers are fully capped prior to harvesting.
Great. All right. So there we have it. What are the 3 mold hive beetle larva and honey moisture content have in common.
Yep,
They're
we
in
now
this
know.
podcast. We now know. You're welcome. All right. Thank you, listeners. And if you have any comments, questions, of course, feel free to email us, contact us on our social media. Let us know if you like some of the content. If you have suggestions for other content materials, let us know. We'd be happy to hear from you.
Absolutely. And guys, don't forget to go to your favorite podcast app and rate us. Rating us is a way that we can help spread the news to other beekeepers and make it available to as many people as possible. So thank you for listening to Two Bees in a Podcast.
Hi, everyone. Thank you so much for listening to this week's episode of Two Bees in a Podcast. We would like to give an extra special thank you to our audio engineer, James Weaver, and to our podcast coordinator, Jacqueline INJ. Without their hard work, Two Bees in a Podcast would not be possible.
For more information and additional resources for today's episode, don't forget to visit the UF-IFAS Honeybee Research and Extension Laboratory's website, ufhoneybee.com. Do you have questions you want answered on air? If so, email them to honeybee@ifas.ufl.edu or message us on Twitter, Instagram, or Facebook at UF Honeybee Lab. While there, don't forget to follow us. Thank you for listening to Two Bees in a Podcast.